across. And then look at this. We're going. Just ramparts, all vitrified, all welded together with molten stone. As we go down lower, the degree of vitrification gets less and less and less until one's down here.
Do you believe this couldn't have been done by tree trunks then? Piled on top of this rock, pile of rocks.
No, I don't believe that for a moment.
Why do you not?
Well, the extent of penetration of the molten rock. These rocks aren't melted, but they're fused in with the molten rock that did melt. So the fire is hottest at its base.
Yeah.
The precipitation should be more pronounced, more defined down here. And yet we're actually seeing material that verges on being loose. Listen. Solid.
Hollow.
Loose. This down here has not been heated up as much as the upper parts. If it was a fire that did this, it should have been hottest at its base, and then the whole thing would have collapsed. Instead, it was hottest at the top, and the thing's melted into itself and set. This wasn't a fire that did this. No way, man. No way. This part of the wall here actually has been too cold. By the time this stuff has run through, it's too cold to have set the stones that were here.
You can see that bubbles have popped the rock here, but there aren't any bubbles in here.
Yeah, the texture of the molten rock's very, very different as you come down, isn't it? It's well spotted, mate. I think it's a good idea to bring you.
It's all cracked here. Solid here. Nearly hollow here.
Look at the cracks in this one over here.
Wow.
Yeah, you see the flames coming up the top. You know you can pass your hand through flames. Yeah, even blue flame. This is hotter. This has been hotter at the top than it is at the bottom. The thing with a furnace or furnace effect that they're expecting to explain vitrification is that the energy from the reacting charcoal is insulated by the heat of the flames above it, so it can build up even greater. Yeah, but when you're using a blast furnace, yeah, all the action happens at the bottom of the furnace. Here, all the action has happened at the top, and the molten slag, for want of a better word, has run through the existing stonework and cooled. Now, this is not what you'd expect to see if you'd got a big pile of logs burning. You would have the hottest place at the bottom, and the thing would start to melt and collapse onto the logs. So all this vitrification, all this molten slag would be underneath a pile of rubble. Whereas here, we've got exactly the opposite. We've got all this molten slag dripping through a pile of rubble. The hottest place is at the top. Now, that's starting to sound more like a nuclear blast again, where the heat from the blast is at the top, and it would melt the rock, which would then bubble down. But
how come it has affected the whole structure of this whole rock?
What do you mean affected it?
Why is there signs of vitrification along all around it?
Here there must have been something else shielding it from the heat. Maybe we've got a cool spot due to the direction of the heat application. Maybe the heat was more intense on the other side.
But it would have, so you're saying it is seeped and has heated the whole thing?
I'm saying it's heated the whole thing at the top. All the molten rock has dripped and bubbled through, shooting all the upper ramparts together.
Okay.
But it's resting on loose rock without vitreous infill. Yeah. And this has happened because it's run from the top, run through. So the fire was hottest at the top. That's where all the heat was applied, at the top, which sounds like an air blast.
Air blast from above.
Nuclear weapon used above, rather than a fire set around the base of the walls. The base of the walls would be molten and it would have collapsed.
You're implying ancient warfare.
I'm implying ancient nuclear warfare. The energy density required to produce this amount of molten rock is something akin to a nuclear weapon. You're talking about megatons of